Firmware is the silent partner in every embedded system, giving hardware its intelligence. It's the permanent software etched into a device's memory, bridging hardware and user commands. From microwaves to spacecraft, firmware drives every action and response. Developing firmware is a disciplined process, far more than just writing code. It starts with planning, requirement gathering, and tool selection. Then comes building the architecture, coding, and rigorous cycles of testing and debugging. Each step is critical. Skipping any phase risks costly failures. Firmware engineers must understand both hardware and software, balancing timing, memory, and power constraints. The goal: create products that work flawlessly for years, often in high-stakes environments like medical or automotive systems. Perfection is essential. There's no room for error. This demands a methodical, disciplined approach. In the next sections, we'll break down the essential steps: defining requirements, choosing tools, and structuring code for long-term success. This is the craft behind the unseen engines powering our modern world. Let's dive in. Every embedded project begins with clear, precise requirements. These requirements are the blueprint for your firmware. Get them wrong, and the whole project suffers. Requirements fall into two categories: functional, what the system does, and non-functional, how well it does it. Functional requirements are concrete and testable, like turn on the heater when temperature drops below set point. Every function, button presses, display outputs, sensor responses must be specified. Non-functional requirements set constraints: response time, reliability, power use, memory limits, and security. For example, respond within 100 milliseconds or use no more than 64 kilobytes of flash. These shape your code and hardware choices. Gathering requirements means talking to stakeholders, challenging assumptions, and demanding specifics. Vague goals like "it should be fast" are useless. You need measurable targets. Document everything in a formal specification. This becomes the project's contract and single source of truth. Without well-defined requirements, you're just guessing. Guesswork leads to failure before coding even begins. Take the time to get this step right. It's the foundation for everything that follows. With requirements set, it's time to choose your development platform and tools. The microcontroller or processor is at the heart of your system. Pick one that meets your needs without excess cost or power use. Reading datasheets is essential to understand each chip's capabilities and limits. Next, set up your development environment: an IDE, compiler, and debugger. Many vendors offer free IDEs tailored to their hardware, streamlining setup. The compiler translates your code into machine instructions for the processor. Connect your hardware using a debugger or programmer probe. This lets you load firmware and debug on real hardware. Installing drivers and configuring the IDE can be tricky, so follow instructions closely. The debugger is your most powerful tool: set breakpoints, inspect variables, and step through code to find issues. Mastering the debugger turns bug hunting into a systematic process. Effective use of these tools saves countless hours. Your platform and environment choices shape the entire project. Invest time here for smoother development ahead. The right setup is the backbone of successful firmware engineering. Now design your firmware's architecture for reliability and scalability. Don't just start coding, plan a layered structure. At the base is the hardware abstraction layer, HAL, handling direct hardware interactions. Above that, drivers provide clean interfaces to components like sensors or displays. This modularity means you can swap hardware with minimal code changes. The top layer is application logic, where your system's main functions and decisions live. Keep this layer hardware independent for easier updates and maintenance. Communication protocols, UART, SPI, I2C, CAN, are vital. Define clear interfaces for data exchange. A modular layered design makes code easier to test, debug, and expand. Build and test small pieces before integrating them into the whole system. This approach manages complexity and supports long-term success. Professional firmware is structured, not improvised. Good architecture is the mark of a skilled embedded engineer. It's the key to robust, adaptable systems. Firmware development is a journey of precision and discipline. It starts with clear requirements, the foundation for success. Choosing the right tools and mastering your environment sets the stage for efficient work. The debugger is your ally, turning bug fixing into a science. A layered, modular architecture keeps systems reliable and adaptable. Separating hardware code from application logic makes updates and testing easier. Each step, from planning to debugging, matters. Mastering this process means building the invisible engines of our world. For those who embrace it, the reward is creating reliable, intelligent devices. This is the true art and science of embedded systems.